Pascal's triangle. Given an integer numbers, return the first numbers of Pascal's triangle. Return the first numbers. Oh, the first. And each number is the sum of the two numbers directly above the addition. So we have to return the row. Okay, of Pascal's triangle. So in this case, we have to return the fifth one. 1, 2, 3, 4, 5. Okay. So, in the case of Pascal's triangle, we have to generate up to the nth row to get it. Right? So, let's see. Okay, output, let's put this in here, right? And, okay, and then 2. Okay, so now, okay. We call this row. This is equal to this. And then all we have to do is the row will have 1 at the beginning. And then for I in range of output minus 1 take the last guy, the length, and this 2. So if we have to get a third row, we need to do 3 minus 2. Okay. See that and I will go from in the case of number of 3 it will be so previous one 2 minus previous one is 2 minus 2 0 0 you want to do the 2. Oh sorry, it's minus 1. Yeah. So in this case it'll be 3 minus 1 which is 2, right? We're gonna get 2 numbers. So it's gonna be I plus 1. Yeah, and then the very end. And 1. 1. And then let's do this. Output we also want to reduce
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve the problem Pascal's triangle. We are given a single integer which represents the number of rows that belong to the Pascal triangle that we want to build. So we want to build a triangle. Let's say we were given a number 5, so meaning we want to build the Pascal triangle with 5 different rows. And this is an example Pascal's triangle that we're given, and you notice that the first row is always going to have a single value. The first row is going to have 1 value, the second row is going to have 2 values, the third row is going to have 3 values, etc., etc. The first value in the first row is always going to be 1, and then we basically build the next rows based on the first row. So, as you can see the definition, each number is just the sum of the 2 numbers directly above it. So this is our base case. Now, what about the value that goes in this spot over here? The 2 values directly above it. Well, the 1 value directly above it, there's nothing there. The other value directly above it is a 1. So we add those together, we get a 1 in this spot. Now over here, the exact same thing is true. There's no value directly over here, but there's a value directly over here, which is 1. We add 1 and 0 together, we get a 1 that goes in this spot. A more generic case, if you look down here at this green cell, you can see that it's 3 plus 1 because when you take a look at the 2 cells directly above it, we have a 3 to the left and a 1 to the right, which is how we can get the value that goes here. So I think the definition on how to actually mathematically build this Pascal's triangle isn't too difficult. But when you actually want to code it up, things can get a little bit tricky because how we are going to represent each row is just going to be a single array. So the first row is just going to be an array of 1. The next row is going to be an array of 2 values, 1 and 1. The next row is going to be an array of 3 values, 1, 2, and 1, etc., etc. Now let's say that we had this row, the row with 3 values, 1, 2, 1, and now we want to build the next row, the 4th row, right? How are we going to build it? Well, the first value in this spot is going to be the 2 values directly above it, right? The sum of the 2 values directly above it. This is in the picture, this is the one that we're worried about, right? There's 1 that's directly above it to the right, but to the left, there's nothing there, right? So how are we going to do this in our code? Well, the easiest way, and this is kind of a trick that I'm going to show you, we can kind of assume that there's a 0 over here, right, in the picture. Take a look at the picture. We can assume that there's a 0 over here, right? Similarly, for this last one, we can assume that there's a 0 over here, right? Because when we add these 2 values together, 1 plus 0, we're going to get the 1 that goes in this spot. So we can assume that there's a 0 at the beginning and at the end of this row, right? Which is going to make things easier for us. Let me show you why. So basically to this array of 3 values, we're going to actually assume that there's a 0 at the beginning of it and a 0 at the end of it. And this is going to make our life so much easier. Let me show you how. So we know we're at the 4th row, right? So we want to compute the values for 4 different spots in this row. Now, how are we going to compute these 4 values? Well, we're going to have 2 pointers, right? We're going to have 1 pointer at the first value in this array of size 3 or size 5, right? This is technically an array of size 5 now. So we're going to have 2 pointers, 1 at the first value, 1 at the second value. We're going to take the sum of the 2 values pointed at by these 2 pointers, 0 plus 1, add them together, we're going to get a 1 in the first spot. Next, we're going to shift this pointer to be in this spot, and we're going to shift this pointer to be in the next spot, and now we're going to add the have created. We're going to be build the draw.
Yeah, the approach is similar to mine, except they're also adding here. So the time complexity is over the square is they're creating n rows, or numerous rows, and that takes like, if you're doing order of n squared times the other. Yeah, let's do remove element. Give an integer array nums, and an integer of val, remove all occurrences of val in place. The order of the elements may be changed. Then return the number of elements in val which are not equal to val. So consider the number of elements in val which are not equal to val to be given. Change initiate a renum such that the first k elements of nums contain the elements are not equal to given the remaining elements known as important. So are we supposed to maintain the relative order? Get confused. Return all occurrences of this file in notes in place. So do you just, so you indicate, let's look at this example, 3, 2, 2, 3, and values equal to 3. So does this mean that you move all the 3's to the end? So I guess we just want to remove it, and you want the first, consider the number of elements which are not equal to kitty except one equal to the following thing. Okay, so it seems like what they're doing is they're putting them at the very end, right? And then they're, so let's see, so let's maybe we have pointers, because anytime you kind of have to move things around in place, you have to use pointers. So if I go until I find the first two, and then I also have a second pointer from the right side, the first non-two. So I can swap this and this, right? And then I find the next, and then I swap this and this. Yeah, I think I can use pointers until, yeah. But then if you have to return, okay, so it seems like we can use pointers. L is equal to the R is equal to right of nums minus 1. So we keep doing this until left is less than right. Okay. While nums L is not equal to val, nums R is equal to val, R minus equal 1. Now we can swap them. So we do this, we go nums L, comma, nums R is equal to nums R, comma, nums L. So now we swap them, right? Yeah. And then you have to return. I guess we can now just always remember. So while L is less than R, while R is less than, no, R is greater than 0 and, right? While when and so you don't want to be able to go out in this case. So what happens is that the value is not even in there, and then you just keep going. Let's see. 3 and 3, well, 5. Oh, okay, right. If you're, yeah, it's not a valid index. So yeah, if L is less than the length of nums, then R is greater than 0. Okay. I mean, we'll break this. 2, 3. So we're here. Compare 2 and 3. That's fine. 2, 2, 3, 2. Oh, okay, so in this case the swap doesn't happen correctly. So what happens is we're here. We go, okay, let's fine. If it was stuck here at the right one, right, the left one, and we'll go to here. The one's 2, 3, 2, and we don't want that. So you want all of them to be. Wait. So the left goes from here to here, right goes to here. Okay, but then you're so smart. Okay, you want left to be left equals the right end. You're still valid. That's the only time you want to be able to swap right here. If the left is less than our end, the left is less than the left. Yeah, this makes sense. That should be a little bit. Yeah. So you only want to swap when left is less than right. The moment left is not less than right? Well, okay, so this will catch it, right? After one iteration. But you have a for loop inside it. So that's all. And that should do it. In terms of time complexity, it's just full of n or n so length of this array. Yeah, that should do it. Let's see.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve the problem remove element. We're given an integer array of nums and a particular value, a second parameter value, and we want to remove all occurrences of this value that we're given as the second parameter. We want to remove all occurrences of it from the other parameter, the nums array. And the trick here is that we want to do it in place, meaning we want to do it without allocating another array. We want to do it just with the input array that we're given. So basically, if you read the next paragraph, since we want to do it in place, the main way that they want us to actually implement this is by taking all the values in the input array nums that are not the particular value. And then place all of those at the beginning of nums. So suppose we had k values in the array nums that are not the value, the special value that we want to remove. Then we would return k, saying that, okay, there's k values in nums that are not that special value, and all of those k values have been placed at the beginning of the array in place. That might seem kind of complicated, so it's best understood with an example. So take a look at this input array that they are giving us, and the special value that we want to remove is value 2. So we want to remove all occurrences of 2 from this array. Now, by remove, they don't just mean delete the value, they mean do it in place. Where do we do?
Hello? 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 Hello?
Do it in place. So in the output, you can see this is what we want the array to look like. So you can see that all the values that are not 2 have been placed at the beginning of the array. The relative order, as you can see, does not actually matter, right? Like 4, 0, 3 is not the order that they appeared in the input array. In the input array, they were given as 3, 0, 4. So it doesn't matter what order we do it, but we have to put all the values that are not 2 at the beginning of the array. But this array, this output array, is not what we're actually returning. We're just returning 5, indicating that there's 5 values in the array that are not 2. And like I said, the trick to doing this is doing it in place without allocating any extra memory, as you can see up above. So returning the value.
I guess you don't even need to do this again. For example, right, all I do is equal to 1. Okay. work. Yeah, and then just return output. I don't have to check it. Oh, it's just like one. Alright. Yeah,
Value itself 5 would be easy in this case, right? It's easy to count which values are not 2, but doing the actual in-place modification is tricky if you're a beginner, so let me explain it. So how would we want to do this? Of course, we can see the first 2 values. These are not 2, so we don't have to do anything with them, right? Okay, the next values are 2, but we can't just delete them, right? We have to replace them with other values that come after them, right? Basically collapsing these values onto the 2s that we want to remove. So we read the 2s, then let's say we get to a 3, right? Where do we want to put this 3, right? We don't know that there's anything else in the array. There could be, there might not be. Where would we want to put this 3? We could put it in this spot, replacing this 2, but it would be much better to put it over here, right? Replacing this 2, because we want to put all of the values that are not 2 at the beginning of the array. So it's better to put it here. So suppose we do that. We replace this with a 3, and you know the real 3 can just stay here for all we care. And then next, we're going to get to a 0. So this is also not a 2. And we'd want to put this over here, right? We know there's another 2 over here. So let's put the 0 over here, right? So basically what we're learning by just going through this example is it might be very helpful for us to keep a
place to find a place. Nope.
pointer, you know, let's call it K or let's call it I or whatever you want to call it. A special pointer basically telling us next time we find a non-2 value like 3, 0, 4, where should we put it, right? Where we should put it replacing the, you know, the 2, wherever the first 2 happens to be. And then once we do that replacement, right, we'll take our I pointer and then shift it by 1, saying, okay, next time we see a non-zero value, like 0 in this case, then put it over here. And then again, we'd take our I and then shift it. But this time, see, our I pointer is at a 3 value. But it's okay for us to, you know, next time we get a 4, to put the 4 over here, replacing the 3. That's perfectly fine, because remember, we already took this 3 and then put it over here. We already shifted it by once. Okay, so that seems pretty simple, what we need to do when we see a non-2 character. But what happens when we do see a 2 character, right? Let's say our I pointer is over here, and then we arrive at this 2. Would we want to put the 2 over here? No, because we only want to put non-2 characters at the beginning of the array, right? We don't care about the actual 2 character. And I've been using I for this, but it's probably better to use K. This K value will actually be the output value that we end up returning in this problem, because this K is going to be incremented every time we see a non-2 value. So it'll tell us by the time we've reached the end of the array, it'll tell us how many values are in the array that are not 2. So that definitely makes sense for us. Now, one thing you might be wondering is, you know, we initialized our K pointer over here, but isn't the K pointer initially going to be at the beginning of the array? And, you know, suppose we didn't even have any 2s at all. What are we going to do in this case, right? We're going to say, okay, we have a 0. This is not a 2, so does that mean 0 is going to be swapped with itself? That doesn't really make sense. And then would we want to still shift our K by 1 because we didn't see a 2 in this position? And you're right, it doesn't really make a lot of sense to do it, but it elegantly does work out with the code, right? For example, if we did not have any 2 characters, right? Suppose these didn't exist and this didn't exist. How would the algorithm that I'm explaining, how would it actually run? Well, we'd see a K, we'd start with a K here. We'd say, okay, this is not a 2, swap it with itself. Okay, then K gets incremented by 1. This is not a 2, swap it with itself. Okay, K gets incremented by 1 to over here. Swap it with itself. swap this with itself, swap this with itself, and then we're done. And then by the end of it, our K pointer would be over here. It would be at position 5. And we would want to return 5 because that's the number of non-2 values in the array. And then this is what our array would look like. We didn't actually modify the array at all if this was the input array itself. So you can see that this algorithm, it's simple, but it does work in all the edge cases that we need it to work in. So it makes sense, and without further ado, we can now jump into the code. Okay, so now writing the code, remember the main thing that we're just going to be maintaining in this problem is just the K pointer. Initially, it's going to be at index 0, and then we are going to just be iterating through every single value in the input array. We're going to be doing that with a pointer I, so let's just get the length of the input array nums, and then do that. Remember, if we see a 2 value, then we're just going to ignore it, right? We're not going to execute anything. But if we see a value that's not 2, or I keep saying 2, but we actually want the second parameter that was given to us called val. So if this is not equal to that special value, that's when we're going to be performing the swap. If we do see that special value, then we can just ignore it, right? We don't want to take that special value and then push it to the beginning of nums. We don't want to do that. And basically from what I'm writing, you might actually recognize that this algorithm that we're doing is kind of similar to the partition of like a quick sort or quick select. By partition, in this case, we're taking all values in nums that are not this particular value and then putting them at the beginning of nums. That's what we're doing when we say partition, if that makes it easier to understand for you. But like I said, so if it's not the...
So what they're doing is the loop through, they don't have but 2 pointers, there's like 1 pointer, right? So in this case, they loop until they find something that's equal to like 2 this case, right? So yeah. So then they swap this 2, and then this becomes a new place for the other one. So it's kind of like this, but it's just you're only using 1 pointer. So not a new lane of nums. If in nums I is not equal to val, let's say, then, but if you get to a place where it's equal to val, so let's say I find it, let's say I get, right, and then what I'll do is, I'll swap it, I'll do nums, num I will equal to nums I, I swapped it, and then I would do L plus equal to 1. But let's say I don't find it, right? So in that case, I don't want to do anything. I just want to keep L as it is. But then from here, okay. Well, this would move it to the here, if it's not equal to val, I do like go to the next one until it is. If it is, in this case, if it's equal to val, then it's move it to the right, correct? Not equal.
Special value, then we can take this and then put it at our index K, which tells us where to put the next.
So what you're saying is that if you move from here, right, straight, if you find the something equal to val, okay, you leave it. Oh, right. So okay, so if you find something that's not equal to val, right, then you would swap it with position L. You would move it to the left. But let's say you find something that is equal to val, right? So in this case, we have 3 swaps with itself. We come here, 2. Okay, 2 is not, 2 is equal to val, so we leave this position for, and then we go here, and then we swap 3 with this, and then, yeah, okay, yeah. And that should be. Yeah, interesting. So I have the approach of using 2 pointers, right? But you can just, well, I guess we are using 2 pointers, so but they're both iterating forward instead of one iterating backwards, the other iterating forward. And it works really nicely because it covers all the edge cases. You know, if so anytime you see something that's not equal to value, you leave it until you see something that's equal to. Anytime you see something equal to value, you hold this position until next time you see something that's not equal to it, then you swap it. Right? Yeah. And that should take care of it. Well, then time complexity, where n is the number of elements in lumps. Yeah. Okay, let's do unique email address. Every valid email consists of a local name and a domain name separated by @ sign. Besides lowercase letters, the email may contain one or more period or plus. For example, hours@leetcode.com, hours with local name, this is the if you use schedule local name or the address, email sender before the same address plus the dots. Okay, name that this does not apply to domain names. Okay. Right. If you add a plus, and local name, everything after the plus will be ignored. This allows certain emails. Okay. Given define array string emails where we send each email and return the number of different addresses that actually receive emails. So we have to filter out like the periods and pluses and then create a set, and then at the end return the length of the set. So you're going to create a set called unique emails, which is going to be some set, okay? For email in emails. So domain comma local will equal to email dot split, and we're going to split it. And I'm guessing that emails are going to be valid emails, right? Yeah. Exactly what we think, it's funny. So now we got a domain right now. So let's do this. In the local, if there is a period, we ignore it. If there's a plus, we simply ignore it. So for that, all I can do is R in, sorry, it's a local, and then R in local. So if R not equal okay, so we got that. There's no rules for domain okay. No email, okay, that's okay. So now we got our unique email. So then we do is we go that should be 45, what day? Oh my god. Oh wait, again, this was something about it. Okay, if you add a plus locally, everything after plus will be ignored. Okay, yeah. If it's this, you add it. Okay. If car is equal to, alright, if you have a plus, ignore it. Break. We break out of it. Kind of this order of the length of the emails. Just a
Hey
nice-
everyone, welcome
just a nice string manipulation question.
back and let's write some more LeetCode today. So today let's solve the problem unique email addresses from today's LeetCode challenge problem. So basically we're given a list of email addresses and we want to count how many unique email addresses there are within the list that we're given and then return that number. Now how do we determine if a email address is unique? Well, first of all, we're told that we're given only valid email addresses where each one has a local name and a domain name, and both of these are going to be separated by the @ symbol that you're probably familiar with, and it will only include the @ symbol, lowercase letters, or the dot symbol, period or dot, and the plus symbol. This example, this email address has a local name, which is this part, and the domain name, which is this part. Now, we're basically told with this sentence over here that the dot character, if it appears anywhere in the local name, then it can be ignored. So basically, these two email addresses below, the local name in the first one has a period in it, and the second one does not have a period. But remember, we were told that period symbols in the local name can be ignored. So basically, we're told that this email address is the exact same. So if we were given a list of 2 email addresses that included both of these email, then we would return the integer 1 because there's only one unique email address in this entire list of 2 email addresses. There's another special case with the plus symbol if it appears in the local name, which remember the local name is the first one, everything before the @ symbol. So if there is a plus symbol in the local name, basically everything that comes after the plus symbol can be ignored. Again, let's take a look at the example. Here, you can see that in the local name, which comes before the @ symbol, there's a plus symbol. And then after the plus symbol, you can see that there's a string name. Now, remember, everything after the plus symbol, including the plus symbol, can be ignored. So pretend like this plus symbol doesn't exist, and pretend like everything that came after the plus symbol up until the @ symbol, pretend like that doesn't exist either. So we're left with m.y. Now remember, dots are also ignored. Period symbols are ignored. So we can erase that as well, in which case we're just left with m and y. So in our local name we have my, then we have the @ symbol, and then we have the domain name email.com, and as you can see over here, that's what the email address is. So basically, if we were given a list, assuming we were given a list with this email and this email, we want to know how many unique email addresses are within this list. We would return 1 because both of these are the exact same. Now, one thing you may have noticed that we can use both of these rules together. When we say both of these rules, we're referring to the plus symbol rule and the dot rule, and that's pretty obvious because we just did that, right? You can see this string had plus and it had a dot symbol, and we used those rules together to simplify that email address. So these 2 emails are considered duplicates. So how can we actually count the number of unique email addresses? Well, once you understand these rules, it's pretty simple. We're going to go through every single email in the list that we are given, and we're going to take that email and then apply these rules to it, the plus rule and the dot rule, and then simplify the email. Specifically, the local name is what's going to be simplified because the domain name really is just going to stay the same. And once we simplify that local name, then we're going to take that simplified email and then store it in a hash set. Why are we choosing a hash set of all the data structures we could use? Because hash sets are going to eliminate duplicates. Because once we take a once we take an email address, simplify it, then we can store it, right? Now, of course, we could have multiple copies of the same simplified email address, and we don't want to store duplicates because we want to count how many uniques we have. So this hash set will eliminate duplicates. Each email will be stored in O of 1 time. We have n emails. So the overall time complexity is going to be big O of n. You could add one more variable to it because we are going to have to parse each string that we're given. We're going to have to, parse it to eliminate characters, split it, do some stuff like that. So you could say n times m, where m is maybe